Alright guys, we're going to look at section 2.5 here, and it's on vectors. And one of the things that we're going to talk about is how to follow something called the parallelogram rule. So you see here it says to find the resultant. The resultant is when we combine two vectors, construct a parallelogram. So this word parallelogram is going to be a key word in here for us today. The diagonal side of the parallelogram shows the resultant. Okay, so when we add two or more vectors together, that is called a resultant. So we're combining two vectors in some kind of way. It's simple when they are parallel. But so if they're in the same direction, we add them together and they just combine to make a bigger vector. If it's in opposite direction, then we subtract them. Okay, so here's an example with Nellie, and she has some tension in her rope equal to her weight. So you can see acting downward here. Nellie's got a 300 Newton vector acting down, and so the tension going down is going to be equal to, or her weight going down is going to be equal to the tension in the rope going up. That's equal to Nellie's weight. But if we cut it in half, and so now Nellie is hung by not just one rope but two, you can see we end up having two ropes, and each one would have half of her weight. So this first rope would have 150 newtons. This second rope would also have 150 newtons. So then the parallelogram rule comes from when we want to find the resultant of things that are non-parallel. So all the vectors we've been looking at so far have either both run up and down, like in the last one, Nellie's vector, we had a tension vector up and a tension vector down, or we've had some going straight to the left, straight to the right. And those kind of are easy because we add them together, subtract them. But how do we deal when we have things that are non-parallel, so they're not running in the same direction? We use something called the parallelogram rule. So if you guys will consider with me, there's two vectors at right angles. So down here we have a 90-degree angle to each other. If we construct a parallelogram, so you can see the picture over here, what we did was we translated or slid this vector up so it touched the tip of this one. Okay, try to get this so it's not too sloppy. All right, we translated it up, and we did the same thing with the second one. We translated it over, and once we've done that, we have been able to create a parallelogram, or a four-sided shape, two sets of parallel sides. And so when we connect where the vectors begin with where they meet at the end, you draw a line through there, this new vector is called the resultant. And the resultant vector, R here, has the total effect that these two red vectors down here have, each on their own by themselves. Now there are sometimes special cases where we have perpendicular vectors. Perpendicular just means they are 90 degrees to each other, like in this case here. And they're equal in magnitude, so if this was 10 newtons acting upward, and this was 10 newtons acting to the right, you can see our parallelogram would end up being a square. So this is a special case where you remember the ratio in a 45, 45, 90 triangle, which is what we have over here. 45, 45, and then we have a 90. The ratio of the sides are 1 to 1, and then the hypotenuse is square root of 2 times bigger. So to get the resultant here, we would take 10 newtons times square root of 2, so this resultant would be 10 times the square root of 2 newtons. So 10 newtons, 10 newtons, 10 times the square root of 2 newtons. Alright, next we have Nellie is going to be suspended at rest from two non-vertical ropes. So these ropes right here are at an angle to each other. And we were asking ourselves, is the rope tension greater or less than the tension of two vertical ropes? So if we change this and had two vertical ropes, if she's suspended by two vertical ropes, we'd say that the tension in each of those, it would be acting upward, and it would be half of her weight. So what's going on when these are not parallel to each other and they're not vertical? So in order to do this, we need to use the parallelogram rule to determine the tension. Okay, so you notice how the tension vectors form a parallelogram over here. So I'll draw this out again. We have the two tension vectors for this situation. So tension acting up like that, and another one acting up like that, and they should be equal to each other. Looks like the angles are equal, but here's the two tension vectors. They kind of give us those. So again, I can translate a vector up here, make it the same length, and then I translate this one over here, sloppy, and then we connect them. There's our resultant. That is the total tension in this rope for Nellie. And so what you can see now is that Nellie's weight is what is acting downward here. You can see she's got some downward force, the weight that she's putting on these ropes, pulling down. And then here's our resultant. And so what you can end up seeing is that Nellie's weight and the resultant vector we get are actually the same. So using the parallelogram rule, we can find that the tension in each of these ropes, so you've got the tension over here, these two resultants is actually more than half her weight because they're spread out a little bit. So when we start to spread things out like this, the tension is going to increase. This tension is going to increase. And you can see that as the angle gets even bigger, so we hang the two scales way out at the sides here. So we got one way out here, and we got another one way out here. As we spread those out, so the tension is acting more and more horizontally now. You can see that the resultant, so this again is the resultant from Nellie. And the way we get that is again by translating these two vectors to make a parallelogram. So you slide this red one over to here, and then you slide this red one over to here, and you draw in the diagonal, and what that gives us is the resultant, and it should match Nellie's weight. She's the only weight acting on this. It's her force. And so you can see, but you see this further these out, and the more horizontal the tension is, the bigger it's going to have to be.